So welcome to a second video on belt drives, second and last video where I would like to study the vibrations of the moving belt. And you can see I want to study the vibrations of the moving belt for the case that the belt velocity is constant, the preload is constant, and the preload is large enough so that the bending influence can be neglected. If you write down the equations of motion for that problem, then you can see that they contain the time derivative, they contain the mixed term from the bending influence, from the belt velocity, and they contain a second order derivative with respect to the displacement from the belt velocity and of course also from the preload, and these two terms are then collected by one. So one could say, because this is merely a constant that changes, the new influence is the second term. However, that influence is tremendous because it couples x and t, and therefore we are not yet in place to apply the Bernoulli separation principle because the derivatives are not separated in terms as before that contain only the time derivative and the space derivative. There's a mixed term. But we also have to apply boundary conditions. We have to add some boundary conditions to that equation of motion. As you can see, that equation of motion has a zero on the right-hand side, though one could say it seems that this corresponds to the situation where we have free vibrations. Like for these combined bending and string vibrations, that they're free vibrations, we also have a zero here. But we can add, and this is also something new, something you have not seen for ordinary differential equations, so for classic vibrations, you can have a time dependence and therefore an influence for the boundary conditions and apply a forcing via the boundary conditions. So therefore I would like to consider with you two sets of boundary conditions for that problem. First, the classical case of free vibrations and the same boundary conditions. I could say the same. Well, it's not totally the same. We'll look at that in a moment. For these free vibrations, namely conditions where we have no displacement and the left and the right part of the belt. However, the second condition, namely that the belt is torque free at these 2 points, is missing, is absent, because we have only the second derivative now with respect to space. Therefore, we need only two boundary conditions, and these boundary conditions, the no displacement boundary conditions, are already enough. There are no boundary conditions for the bending torque or something, because we are not dealing with bending anymore. So therefore, this would be the corresponding boundary conditions to what we studied in the last video. And the other one would be that we have an harmonic excitation by one disk. Could be also two disks, but it's sufficient to study just one disk to show the effect. And that harmonic excitation could, for example, come from an imbalance of that disk that then would lead to these, so the disk rotates and there's a rotating imbalance, and that could lead, for example, to these harmonic excitations. So you can see the left disk, so the displacements of the belt for the left disk is zero as before, but for the right hand side we have a displacement because the disk itself displaces in transverse direction. Okay, so and the general problem we have to face first is that the separation method is not directly applicable due to this term here. So how can we deal with that problem? And after we solve that problem, then we can of course solve the equation of motion and apply these boundary conditions. But first we have to know how to do that. So therefore I would like to go back once again to that case where V0 is equal to 0 and consider with you a different way to obtain the solution of the equation of motion for the belt at rest. In this case, of course, I neglect bending. because I want to work with that equation of motion just to show you a different way, and maybe that way highlights a little bit a solution possibility, how to apply the separation method when such a term is present. So let's have a look at the equation of motion once again with v naught equal to 0. So belt at rest. Vtt minus c squared vxx is equal to 0 because we are considering now only the preload, and c squared is then f divided by mu. Maybe that equation is known to you. It's the famous wave equation. The wave equation is usually solved by a transformation of variables. So instead of having space and time separated and then leading to separated functions, as in Bernoulli's separation method, one can also do the opposite. Add them together, namely formulate x plus ct and x minus ct. Let's see how this applies to our equation of motion. Therefore, we have to transform the derivatives. Let's start with the first order derivatives. So instead of d by dt, we find du by dt, which is c, d by du, and then we have plus dv by dt, which is minus c, so therefore the negative sign here, d by dv. So this would be d by dt. For d by dx, we have the same. D by dx is then d u by dx, d by du, and which is then equal to 1, and dv by dx, which is equal to 1, d by dv. Now we need second order derivatives here with respect to time and to space. So therefore, we apply the derivative with respect to time once again to the transformed derivative. So transforming that derivative then once again leads to something that could be a binomial formula also. C squared d squared du squared minus twice d squared, the mixed term du by dv, and then d squared d by dv squared. And for d by dx, it's the same. It would be also a binomial formula. Second derivative with respect to u plus twice the second derivative with respect to u and v plus second derivative with respect to v. If you would apply this into the equation of motion, you would see that for the time dependence, you have to multiply everything by c squared. However, for the space dependent, the c squared is already furnished by that factor here. So you get the same quantity, c squared, you could also divide by c squared then, by the way, and you then just check the derivatives. They appear, always the same order appears once for the time dependence or the time derivative and once for the space derivative here, but with the negative sign. So all the terms that have an opposite sign will cancel. That is, these derivatives with respect to u and these derivatives with respect to v will cancel, and only the mixed derivatives will be there. You could say they have to be added to 4, but you divide by that factor of 4 as you divide it by the c squared, and you obtain a very simple equation, namely it's the second derivative of w with respect to u and v is equal to 0. This one, written in index notation. W with respect to u and v is equal to 0. A very, very simple equation that is very, very easy to satisfy. Namely, you take a function that depends solely on u or solely on v, and you can be sure that it satisfies the equation of motion and transform variables, and therefore it also satisfies the classical equation of motion if you plug in x plus ct for u or x minus ct of v. This is shown on the next slide. So the transformed equation of motion is v, w u v is equal to 0. A general solution would be composed by functions u and g that are twice continuous and differentiable, but depend solely on u and solely on v, because if you take for that function f of u, if you take the derivative with respect to v, it will vanish. If you take from that function of g, if you take the derivative, when it comes to the derivative with respect to u, the result will vanish, So the final result will vanish. That seems to be a little bit strange, right? We are used to compute a solution in explicit form containing, for example, cosine or sine function or exponentials or whatsoever with some nice integration constants, and then we determine these integration constants, and at the end we are happy because we have that solution in explicit way. Here you get some kind of, I would say, a little bit indirect way to write down the solution. It's not, you cannot really grasp it because you do not know what the function f and g is explicitly. It could be any function. It could be, for example, you can start with a polynomial in u and with a polynomial in g. But then what would happen if you sum up all these terms? Would you be able to see something? How would you adapt this to boundary conditions and so on and so on? Many questions. But first of all, we get an idea of what we could do with our real problem that we want to determine, namely how to get rid of the mixed term. Here you get something, how do you produce that mixed term? If you hadn't one, maybe the opposite way would lead to the loss of that mixed term. So transformation seems to be a good way. And we can derive some physical properties, and we get some physical insights from that general solution, namely an interpretation, it's a wave equation, and interpretation of the solution as a wave. That's something that is hardly visible if you decompose that wave in the solution into modes, mode shapes, and natural frequencies. So this is the advantage of this approach. So you see that these functions are waves that propagate either to the left or to the right. Why? Well, let's look at the wave propagation. You can be sure that that function will reproduce the same value if the argument is the same. So if x plus ct is equal to x1 plus ct1. However, you can change x independently from t. So if you fix just one quantity, or if you select to move one quantity t, if you move the quantity x, you will get to a point where fx plus ct is equal to fx1 plus ct1, and thus where the solution has the same value. Yeah? Well, how should I change that? Well, if you solve that equation, so you put everything, again, everything containing x on the left-hand side, everything containing a time t on the right-hand side, you see if you change t, let's say from t to t1, you should change x, according to this equation, to x1. Now, how do you change this? Well, if you increase t1, you get a negative sign, you get a positive sign here, so you have to decrease x1. On the opposite, if you decrease t1, you have to decrease t1, you get a negative sign here, so you have to increase x1. The best is to look first at the limit value. So you can formulate then a velocity by taking t minus t1 to the left-hand side. And what you then see is you get x minus x1 divided by t minus t1. You take the limit t1 to t, and you get the velocity of that wave, and the velocity is negative. That is, the wave propagates to the left. If that wave propagation velocity is positive, you propagate to the right. So f is the wave that propagates to the left. G is the wave that propagates to the right. Let's visualize this. Let's take some kind of test function, a bump function. Such a function with a small hill. It's now difficult to visualize because we have a three-dimensional, reduced of course to two-dimension, a plot here containing x, containing the time t, and containing that function f. So every representation shown here corresponds to a different time t. So we move, let's say, in the background, in the direction of the t-axis with these functions. Each function is the same function, this bump. That bump occurs at time or at point x equals 0, so the maximum of that hill would be at x equals 0 for the first time, t. Now I move to the next time, to t1, so I move forward on the time axis. My figure moves backward on the space axis, that function f. If you look at that hill and if you project it correctly, or here would be the maximum position of that hill, you end up with the position at minus c1, t minus t1, and if you take this value, then you would sit here. So that figure moves then to the left direction. It's a wave that moves to the left direction. No? So you get a physical idea of what that solution represents. It represents, so the belt, it would be a wave that propagates. One part of the solution propagates to the left direction, the upper part of the solution propagates to the right direction. Well, that's the basic idea. And now, with that idea of the wave equation here in mind, we would like to do something similar for the moving belt, namely apply transformation of variables, and at the very end we would also like to have the two interpretations. First, we would like to get an idea of how to solve then the equation by the Bernoulli separation, and finally we would like to get an interpretation by wave functions of that solution for the moving belt. Okay, so let's do that. Let's start with the wave equation for the moving belt, that equation, and for the transformation of variables in order to get rid of this term here. With the mixed derivative, I would propose the following. Let's fix time x, but let's work with, let's fix space x, but let's work with the space-dependent transformation of the time, q and u, time variable. That transformation is decomposed by v naught, which is the belt velocity, so changing the belt velocity, and with the difference, so to have the c squared minus v naught squared factor here, c squared minus v naught squared in the denominator. Let's look at the transformation of variables for this situation. So for the first derivative with respect to time, we have d by dt is equal to d by d tau. The only way to get a derivative with respect to time is here from the second term, and dt by d tau is then 1. And for d by dx, we have on the one hand d by d psi, but we don't have to forget this one here, which is d by d tau, d by d tau, dx by d tau by dx, and d tau by dx is v naught squared divided by c squared minus v naught squared, and for this I incorporate another abbreviation, namely c squared minus v naught squared divided by v naught is then v tilde, so that we have 1 divided by v tilde here, d by d tau. We need the second order derivatives here. The first one is the second order derivative with respect to time, which is quite simple. It reproduces the second derivative with respect to tau. The mixed derivative is now composed by a time derivative, I could say, of that expression here, which then leads to a mixed derivative in psi and tau, and to a mixed derivative 1 divided by v tilde d squared divided by d tau squared. Here it is very important that neither c nor v naught depend on time. That one here. And finally we have the second order derivative of dx. It's well done, similar to, again, a binomial formula. The second derivative with respect to psi, a mixed derivative 2 divided by v prime d squared d psi d theta, and 1 divided by v tilde squared, second derivative with respect to theta squared. No, with respect to theta. Okay, now we plug in these second order derivatives into the equation of motion, and we will convince ourselves that the mixed term will be lost then, and that we get an expression where we can apply Bernoulli separation. So we transform the equation of motion by application of these second order derivatives, and once again v tilde is noted here, it's c squared minus v naught squared divided by v naught. If we plug in everything, we get first the second derivative with respect to theta. We then get a term that contains 2v naught, the mixed derivatives, so it's the second derivative of psi theta here, and it's 2 times v naught divided by v tilde, v w theta theta theta. Finally, for the last term, we get minus c squared minus v naught squared. And this is represented by multiplication of v0 by v tilde, so that we get the c squared minus v naught squared of the numerator only, times the second derivative with respect to psi. For the next term, we get minus c squared minus v naught squared, which is then divided by v tilde. So the numerator cancels then with the denominator of v, or the denominator here in the term v tilde, so that we get v0 here 2 times, minus 2 times v0 w theta psi, or psi theta, and for the last term we get minus v naught divided by v tilde, and it's the second derivative here with respect to theta. So there would be, at the moment, there would be a mixed term in psi and theta, but we are happy to see that this term cancels. So indeed all the other terms contain derivatives with respect to theta and with respect to psi only. So here, this one. So we already see that the mixed term goes away and that we can apply here Bernoulli separation. But we will of course summarize the terms containing the derivatives with respect to theta, second order derivatives, and the term containing the second order derivatives with respect to psi. Well, with respect to psi, it's quite simple. There's just one term. With respect to theta, we have a coefficient of 1, a coefficient of 2 times v naught divided by v tilde, minus a coefficient of v naught divided by 2 tilde, v tilde. So if we add these two terms, then we arrive at 1 plus v naught divided by v tilde times w theta theta minus v naught v tilde w psi psi. Well, this term here in parentheses can be simplified to be, you have v tilde, that is c squared minus v naught squared divided by v naught. So you have v naught squared divided by c squared minus v naught squared. For 1 you have c squared minus v naught squared divided by c squared minus v naught squared, yielding in total c squared divided by c squared minus v naught squared. So this will be the leading factor of the first term. And then, of course, we can divide by this leading factor in order to have the so-called time derivative, but you can see it's really equivalent to the time derivative without any leading coefficient. So in the form of a wave equation, and then interpret the other factor in front of the second order, which is not now a real space derivative. So here one has to take this in parentheses, perhaps, that term. But we can interpret then the coefficient as the wave propagation coefficient. So in transformed variables, we get w theta theta minus, and if you divide by this term, c squared minus v naught squared divided by c squared. If you do all the computations, because v naught divided times v tilde yields c squared minus v naught squared again. So you get c squared minus v naught squared squared, and you have a c squared, so you can summarize everything to c squared minus v naught squared divided by c squared. And this would be the new, let's call that c tilde, the new wave propagation velocity of that wave. And what you can see is already here, the influence of the belt velocity. So you can see that the belt velocity reduces the wave propagation velocity. Theoretically, but really theoretically only, that wave propagation velocity could become negative if v naught is larger than c. But if v naught is larger than c, then we are not talking about a good belt drive where we have a high preload and there is no slip, but this would exactly be a condition in which we would have slip and in which the preload would be too low. So therefore, such high belt velocities can be included, are not realistic. So in reality, that wave propagation velocity is a positive constant. So once we have that positive constant, we can now solve the transformed equation by Bernoulli separation. So then we have two ordinary differential equations where, and this is the important point now, the space dependence, so the derivative refers now to psi and the dot refers to the derivative with respect to theta, where the ordinary differential equation that describes the space behavior is now much simpler than in the case before because we have no bending. So both equations lead to harmonic solutions with sine and cosine terms. The first one is the classical equation for vibrations with the natural frequency omega. The second one could be also seen as an equation that describes a single degree of freedom oscillator, but it's related to space dependence or to dependence on psi. But the solution would be expressed in the same way. So instead of theta, you write a psi here, and instead of omega, you have to write omega divided by c tilde here. And c tilde was the changed wave propagation velocity, or influenced by the wave propagation velocity influenced by the constant belt velocity. So according to our solution procedure, we now have to specify our boundary conditions, and we have to apply the boundary conditions to the second equation in order to determine the values of omega, these natural frequencies. And again, if we do this, so this was our general solution, the boundary conditions for free vibrations are first boundary condition on the left-hand side, where this one is the same for free and for forced vibrations equal to 0. We immediately get that CF3 must be equal to 0. So the second term will vanish for x, and therefore psi equal to 0, as psi is equal to x. And leading then to C3 equal to 0. Now, non-trivial solutions are obtained if we apply the free vibration boundary condition, so the no displacement boundary condition also to the right-hand side, by a condition omega n tilde equal to n pi l times c tilde. So the complete solution, again, you take then the mode shapes, which are then the sine harmonic terms, where you include omega n tilde according to n pi divided by l c tilde here, where you then replace omega here by omega n in the time-dependent behavior, and where you substitute the transformation of theta back to t plus x divided by v tilde here for the harmonic behavior. And what you can see now is that in the usually time-dependent term, there's hidden one additional term that depends on space in these cosine and sine function. One could interpret these terms as being somehow phase shifts to that time-dependent behavior, omega nt, and these phase shifts are then, let's say, position-dependent or dependent on that point and that position x under consideration. Still, there are two setting of integration constants here coming from C1, C2, which is then multiplied by the constants, well, of the mode shapes, of the various mode shapes, so C4n, for example, leading to two sets of integration constants, Cn, n, and C2n. And again, there are countably infinitely many of these integration constants. So again, we need orthogonal relationships for the mode shapes. They are not difficult to obtain. They are, well, can be obtained with the same arguments as before. We have orthogonality relationships for the sine function. Our sine function contains an integer number n, and for different integer numbers, therefore, we have that orthogonality relationship. So everything the same as before. What I would like then therefore is to stop the discussion of the complete solution here and rather to focus on the differences now and on the interpretation of the result. The first interpretation can be already done regarding the natural frequencies. So we can compare the natural frequencies for the moving belt to the natural frequencies we had before for the belt at rest. The difference of these two natural frequencies must sit in the C tilde here, because before we had the same reasoning, n times pi divided by L as here, the same factor, but multiplied by c, the wave propagation velocity for the belt at rest. We take therefore the ratio of these two expressions, then this factor goes away, and we just have the ratio of c tilde divided by c. Now what is this ratio? It's c squared minus v naught squared divided by c squared. Yeah. So we leave that c, but we have to, for c tilde, we had c squared minus v naught squared divided by c. So therefore we have c squared minus v naught squared divided by c squared, which is then 1 minus v naught squared divided by c squared. So you can see that the belt velocity not only reduces the wave propagation velocity, it reduces at the same time also the natural frequencies. However, usually this effect is small. So usually the natural frequencies, they are reduced, but they are reduced by a small factor because v naught is much less than c in practice. Once again, in order to avoid that the belt slips around the wheel. So this would be the interpretation with the natural frequencies in the sense of Bernoulli separation theorem. So we have seen how the solution then can be produced. And now the question is, how can we interpret this in terms of wave propagation? Once again. So how can we interpret the natural frequencies or the first natural frequencies by looking at the wave propagation? Well, if you look at a certain particle, at a certain place, and you look at the propagation velocity, then in direction of rotation, you have the propagation velocity of c plus v naught from the velocity of the belt. In the opposite direction, you need c minus v naught, the velocity of the belt. So the travel time of a wave, so to travel to one wheel and then back to the other wheel and back to its starting position, is you travel 1 times the whole length in forward direction, so direction of rotation, 1 times in backward direction, and you have to add these two results. So the total travel time of a wave from one starting point is the whole length in direction of rotation, so divided by c plus v naught, plus the whole length divided by the velocity in opposite direction, which is c minus v naught. Well, let's add this. So we have 2 times LC. We have to multiply here with the first term with c minus v naught, the second term with c plus v naught. So what we get then is we get the terms in c plus v naught and c. the terms in L times V naught will cancel because they appear in opposite sign, and we get just twice the term LC in the numerator and C squared minus V naught squared according to the third Bernoulli binomial formula, C squared minus V naught squared in the denominator. And if you look at that expression, C squared minus V naught squared divided by C in that sense, so in the denominator, taking the C of the numerator into account, you find again the change affected wave speed, wave propagation velocity of the moving belt. So we get 2L divided by C tilde. If you take then the reciprocal of that value t, you would arrive at a certain period, namely the period that a particle travels, the wave travels, and then it would restart its motion. So this must be a fundamental period. Let's compute it. 1 divided by tau is equal to C tilde divided by 2L. And what is C tilde divided by 2L? If you look at omega 1, it contains this C and then the factor of pi and divided by L. So it's omega 1 tilde divided by 2 pi. So this would be within the period of the first fundamental natural frequency. So with this, you have the link between the wave propagation velocities, so the wave propagation interpretation on the one hand side, and the interpretation in natural frequencies. It's the traveling time is the period of the first fundamental mode or natural frequency given by the wave propagation velocity, taking of course the velocity of the belt into account. Now that's everything I would like to tell you about the free vibrations, but we have a second part that is related to the forced vibrations. That is, the first boundary condition is still the same, but the second boundary condition changes. And now again, we have to find a particular solution that matches with the boundary condition. So what would be the particular solution? So we said that omega, which is now not the natural frequency, but which is given by the motion parts of the imbalance, or by the, at least by the displacement of the wheel, omega. It's given by the forced motion of the wheel, and therefore by the boundary condition. It's now an excitation frequency. We still assume that we have that harmonic solution. Why not? That's what the Bernoulli separation yields. The same holds for omega, for W with respect to psi. Also there we had a second order ordinary differential equation, which we of course have to satisfy. But now that constant omega is not a natural frequency anymore, but it is dictated by the boundary condition. So it's the excitation frequency, and that is, I guess, related to the rotational frequency of the disk, if one is looking to a mechanism how to get that excitation frequency. So the boundary condition, well, the first one is the same as before. Well, therefore the result must be the same as before. C3 will be switched off, will be equal to 0, so we get here only the term in C4. So, well, if we then multiply that function theta and W to get the complete particular solution after application of the first boundary condition, we then have two constants left. You see, I transformed here back to time and space by replacing theta by t plus x divided by v tilde. Well, same for psi. And now we have these two constants, and one would say, but we just have one boundary condition, right? How can we determine two constants? Well, we can, because we can compare coefficients in sine and cosine terms. So let's apply that boundary condition. You see, it's a cosine harmonic function. On the other hand, in our setting, we have cosine and sine harmonic function with respect to time. We can make a comparison of coefficients in time, cosine omega t and sine omega t, and we then have two equations, algebraic equations, to determine the two integration constants c sub 1 and c sub 2 from this one single boundary conditions. Therefore, we apply addition theorems for cosine and omega. So the classical Engel addition or addition theorems for harmonic functions. So we replace the cosine of omega t plus L divided by v tilde by cosine omega t, cosine omega L divided by v tilde minus sine omega t, sine omega L v tilde. The same will be done for the sine function, sine omega t, cosine omega L divided by v tilde plus cosine omega t, sine omega L divided by v tilde. And we equate the coefficients, where the factors in front of the cosine omega t and the sine omega t. Let's look at this. So for the sine omega t, you find the contribution from the cosine function, the second entry, so with a negative sign, with a c1 times sine omega L divided by v tilde, minus c1 sine omega L divided by v tilde. From the second term, from the decomposition of that sine function, you will find a contribution in, looking for the sine omega t, in cosine omega L divided by v tilde times c2. Well, and on the right hand side, you will find nothing. No contribution in sine omega t. So therefore a 0. You can then ask, but where is this term? Well, let's divide by this term. So by sine omega L divided by c tilde, that is, it must appear now in the second equation on the right hand side, because the second equation will be the equation for the coefficients or for the factors in cosine omega t. Here it is. Sine omega L divided by c tilde. Okay, so we found already the right hand side. Let's check the left hand side. So let's look at the terms in cosine omega t. For the cosine function, it's cosine omega L divided by v tilde times c1 here. And for the second term, it's sine omega L v tilde times c2, so this one. So two algebraic equations for two constants c1 and c2. So solving these linear equations is easy. I skip therefore the step and present the results. What can you learn from these results? Well, you can see that these coefficients now include the cosine and the sine functions, and you can see it. They include also the sine omega L divided by c tilde in the denominator. What can be said about that? Well, there could be resonance, right? Resonance usually would be obtained if an excitation frequency matches a natural frequency. What happens if that excitation frequency omega matches a natural frequency? Well, then that sine function, because this was the condition for the three vibrations, our transcendental equation to determine the eigenvalues, and there with the natural frequencies, that this function, this sine function, then vanishes, leading to, if these are, well, kind of amplitudes, but leading to coefficients c sub 1 and c sub 2, which are infinitely large. So therefore resonance is present, and well, the resonance can be clearly found here for the argument of the sine function being equal to 0, so for omega equating a natural frequency. What else can be seen? Well, we can add our particular solution and again then sum up these terms using addition theorems for the sine and the cosine function. And what you can see in this representation is that if you then interpret this as an amplitude, and again this is the time-dependent behavior, with something that has a phase shift, and the phase shift is not position dependent, that not only the phase shift is position dependent, but also the amplitude or the magnification factor then becomes position dependent here in that particular solution. And that we have standing waves, namely that there are nodes, positions, x, where the amplitudes are equal to 0. And these nodes appear at omega x divided by c, so the argument of the sine function is a natural number times pi. Then the amplitude will vanish, so there would be a node, a value where the amplitude, well, I could say is minimal, is 0, vanishes. The phase shift, as I said, is space dependent. There is resonance for the sine of omega L divided by c tilde. It's even better to see in here, but this is the only term in the denominator. And this is the condition where an excitation frequency corresponds to a natural frequency. So again, we see how these two interpretations, by waves on the one hand, and by natural frequencies and modes on the other hand, how they correspond, or how both interpretations are in fact needed in order to get a full picture, a full idea of what the physics of that solution is. And that's what I would like to show you. So when you look back at what you learned now on the belt drives, is you have seen a general procedure how to obtain the solution according to Bernoulli separation. You need the following steps: solve the ordinary differential equation, adapt it to the boundary conditions. From the adaptation to the boundary conditions, you get the conditions for the natural frequencies, and then sum up the whole general solution and compute from orthogonality, or by means of orthogonality relationships, compute the integration constants from the initial conditions. That's one way. And the second way is interpret that solution as a wave, as its physical properties. Well, and for the moving belt, you have seen that the velocity of the belt affects the wave propagation velocity on the one hand. It reduces the wave propagation velocity. It reduces also the natural frequencies. So again, both interpretations, but that effect is quite small. And you can see that for forced vibrations, you can interpret them as standing waves, as a solution for the particular solution where the amplitudes and the phase shifts become now position dependent, and therefore these nodes are possible. And finally, you can find resonance there. Well, that's all I would like to tell you about belt drives. That was a nice introduction. I hope nice for you also. But I guess a good introduction at least to a theory of continuum vibrations. And we will continue in this sense and learn more about continuum vibrations in the next, and it's the last chapter, which deals then not with belt drives, but with blade vibrations. So we go back to rotors. I mean, some rotors were also included due to the wheels. So we will go back to turbines and to turbine blades and study the vibrations, bending vibrations of turbine blades. Thank you very much for your attention.